Dijkstra's algorithm is a link state-based routing algorithm where every node in the network knows the complete network topology, that is, the cost of every link in the network. Based on these costs and the topology, each node computes, in Dijkstra's algorithm, each node computes the minimum cost route from itself to every other node in the network. So let's begin by studying Dijkstra's algorithm. So the algorithm works by keeping a set kappa. This is the set of nodes to which the minimum cost paths have already been determined. This set kappa is updated at each iteration. Initially, the set kappa is initialized as the node U itself. Remember, we're running Dijkstra's algorithm at node U. Node U knows the costs of every link, Cij, that is in the network. For all links ij that are in the network, the cost of these links Cij are inputs to the algorithm, and as I said, the set kappa is initialized as U itself. Now, initially, for every node in the network, we set the values of the parameters WUI and PUI. WUI is the current cost of node I from node U, the current cost of going to node I from node U. This is initialized as CUI if the link UI is already present, meaning node I is a neighbor of node U. Otherwise, WUI is initialized as infinite because currently the cost of going to node I is not known. So in other words, node U initializes the costs of all of its neighbors to the respective cost of those links because it already has a way of going to its neighbors in one hop. Now, the set PUI is the set of previous hop neighbors on the path going back from I to U. Okay, so the previous hop neighbor for every node, for every neighbor of node U is U itself. Okay, so if node I is a neighbor of node U, PUI is set to U. Otherwise, PUI is set to -1. This is the initialization step. Okay. Now we go to the iterations. The iterations will continue until the set kappa includes all the nodes in the network. Now, the first thing to do in every iteration, find a node I star. I star is a node in the current set of nodes that have not been included in kappa yet, such that this node currently has the minimum cost to node U. So among the nodes that are outside of kappa, the algorithm picks one that has the minimum distance to U, where ties are broken arbitrarily, meaning select just one of those, such minimum distance nodes. And then include this node I star in kappa. Okay. After we do this, we go and reset all of the weights that belong to the nodes outside of kappa. So if the current weight of a node is larger than the weight of node I star, the cost from U to I star plus Ci star I then update the cost of this node I to the cost that would have been obtained if we go to I star first and then go from I star to I, where of course on this path the previous hop neighbor would be I star, so we reset the previous hop neighbor of I, which is P sub ui, to I star. So basically in one iteration we added one new node to kappa, and we continue these iterations in steps 8 through 12 until we have gone through and included all the nodes in the network. Let's see an example. In this example, we're running Dijkstra's algorithm at node A. A wants to find the best hops, the shortest hops, meaning the minimum cost paths, from itself to every other node in the network. For this, it is clear to see that once it finds the shortest minimum cost path to D, it will have found the minimum hop cost paths to every other node in the network. So we initialize by including only node A in kappa. Its distance to itself is clearly 0. And then we initialize, remember, in steps 3 to 5, we initialize all the other WUIs and PUIs. The neighbors of A are B and G, so we go and set the cost WAB as 2 and WAG as 6. And clearly the minimum, the previous hop nodes for B and G are A itself. Okay, and now the other costs are all infinity. So we start the initialization, we start the iterative steps. In the first iteration, remember, we find a node that currently has the smallest weight outside of kappa. This node is B. Okay, B is included in kappa, and now we will reset all the other weights and PUIs. Okay, now that B is included in kappa, the weight of C can be updated as 2 plus 7, 9, where the previous hop neighbor is B. Similarly, we can update the weight of E to 2 plus 2, 4. And this is it for this iteration, essentially. Now, we have an enlarged set of weights, and in the next iteration, we will select one of G, E, and C. Okay, so out of these, E has the smallest current cost, so we select E, and then we update all the other weights. Specifically, F is updated now. G can also be updated because the cost of E is 4. From E, we can go to G with a cost of 1, so we can now update the cost of G from 6 to 5, and we can update the previous hop neighbor from A to E. So although the number of hops have increased from 1 to 3, the cost to node G has now reduced. Okay, so as Dijkstra's algorithm runs, although the set kappa never changes, I mean once nodes are included into kappa, they are included for good, before they're included into kappa, their costs and their previous hop neighbors are subject to change. Okay, so now which node to include in the set kappa next? Well, I guess G, because it has the smallest cost. So G is included. Now we can update the cost of H, for example, to 9. And now let's include the next one, F, because it has the smallest cost. And we can then update, let's see, the cost of C does not change. The cost of H is going to be reduced to 8. And now that this is 8, the next node to include in kappa will be H. And then we can update the distance of D. And now C and D have distances set. Among these, we select C. And then finally, we select D. And we're done. Now, we can trace the shortest path from D to A by starting at D, going to the previous hop neighbor, which is H, and then the previous hop neighbor, which is F. In F, the routing table at F, the previous hop neighbor to A is listed as E, so we go to E. At E, the previous hop neighbor is set to B, so we go to B and to A. Let's do another example. In this example, we're again computing the routes at A. So we start the initialization with kappa being equal to A, and the two neighbors of A, B and D, have finite costs set. Now between D and B, of course, D is going to be selected. So after the first iteration, D already has a cost that is fixed permanently. Now that D is selected, we can update the weights. The weight of B is not updated, but we go to the other neighbors of D, which, well, there's only one other neighbor, which is E. The cost of E is set to 6. In fact, if this link BD had a weight that was less than 1, the cost to B via D would have been less than 3. So then the cost of B would have been updated. Okay, but currently it isn't updated. All right. Now, after the second iteration, A and D are included. The next one, which has the smallest cost so far at this point, is B. So we include B. Once we include B, we update the distances of C and E. Now between C and E, which are the nodes that are currently not selected into K, E has a smaller cost, so we select E and update the costs of C and F. And now C is selected, and then finally F is selected. Now, once Dijkstra's algorithm has terminated, we can find the path from A to every other node by backtracking through the final values of P sub AIs. For example, to find the path from node A to node F, we note that PAF is E, PAE is B, PAB is A. Thus, the minimum cost path from A to F is given by A to B to E to F. So the cost of this path is given by the final value of WAF, which is equal to 6 in the table. So let's see. Now, for any routing algorithm, we need to prove that it works correctly, right? So this theorem summarizes this idea. The theorem says that Dijkstra's algorithm, as we described in the previous previously, satisfies the following properties after the kth iteration. Property 1 is the set K contains K plus 1 nodes. Why is the size of K plus 1? This is quite trivial actually, because initially the size of set K is 1, and in every iteration it is increased exactly by 1. So after K iterations, the size is K plus 1. This also shows that if the size of the network is n, there are n minus 1 iterations. All right. So property 2 is more interesting. For each I in kappa, okay, for each I that is included in kappa, the cost Wi set by the algorithm for this node is equal to the optimal cost. That is, the minimum cost from node U to node I. Once node I is included in the set kappa, its cost is the final minimum cost. Thirdly, for any nodes I and j such that I is in kappa but j is not, the final minimum cost of I is not more than the final minimum cost of j. That is, the minimum cost to a node outside of set K is higher than the minimum cost to a node in the set K. So this tells us that Dijkstra's algorithm iterates on the path length. As Dijkstra's algorithm runs, we include nodes that are further and further away from the source. Let's prove these properties. As I said, well, first of all, at the initialization, meaning iteration 0, the properties trivially hold. We will use induction for this proof. Suppose the properties hold after iteration k minus 1. We will show that they also hold after iteration k. Now, as I said before, property 1 holds clearly because exactly one node is added into kappa in each iteration. Now, consider the following set. We'll define the set S as the set of nodes j that are not in kappa after iteration k minus 1, whose final cost are minimal. That is, the set S is the set of nodes that have the smallest true minimum cost among those that are not in kappa k minus 1. Okay. Now, we may not know which these nodes are, but suppose this is the set of nodes. Okay. Now, we observe the following for these nodes I star. For these nodes j in S. For every node j in S, the previous hop node to j on a minimum cost path must be a node in kappa k minus 1. Let me repeat that. For every node j in S, the minimum, the previous hop node must be a node in kappa k minus 1. Why is this true? By the way, let's call this previous hop node PUJ star. Why is this true? Well, assume it wasn't a part of set kappa k minus 1. Then the true minimum cost node to PUJ star must be larger than to node j. That is, if node PUJ star is not a part of kappa, okay, then since by definition it is on the previous hop node, its cost must be smaller than that of j, but then j would not have been included in the set S. J would not have been a minimum cost node. So this is a contradiction. So this means that for every node in set S, the previous hop node must be a node in the set kappa. Okay, now that we established that, let's look at the following set of inequalities. WJ star is less than or equal to WJK minus 1. Why? Because at the k minus 1 iteration, we may have updated, reset the weight WJ, and when we reset something, it can only decrease. But when we do this reset operation in lines 11 to 13 of Dijkstra's algorithm, we do it as the following. We find the node in kappa k minus 1 that minimizes WUI star plus CIJ. Okay, and we set that I as the previous hop neighbor of J. So then by definition, WPUJ star plus the cost from the previous hop neighbor of J to J is set as WUJ star. So we reached this equality, which shows that for any node in S, the cost WJ star that is currently the cost of this node at the end of iteration k minus 1 is actually the final cost, final minimum cost, the true minimum cost. Okay, but then for any L not in kappa k minus 1 and not in the set S, that is those nodes in those nodes that have not been selected into kappa so far and that are also not the minimum cost nodes. For them, their current weights WL k minus 1 are larger than or equal to their eventual weights. Why? Because by definition, WUJ k minus 1 is the optimal cost, and as they have not been selected into set S, their current cost and their eventual true minimum cost is larger, strictly larger than Wj star, which is less than or equal to their current cost. So hence, at the kth iteration, the algorithm selects a node in set S. Once a node is selected into set S, it stays there. It selects a node in set S into kappa, and once this node is included in kappa, it's there forever. Its cost is not going to be updated again. So properties 2 and 3 of the theorem follow from the induction principle. Okay, now computationally, Dijkstra's algorithm has complexity n squared, where n is the number of nodes. Why? Because in a network with n nodes, the algorithm terminates after n-1 iterations, as I said before. And in every iteration, there's order n computations, because in every iteration, we are going through order n nodes. That is, we are selecting among n nodes, essentially order n nodes. Now, the drawback of this algorithm is that it requires each node to know the states of each link. But in modern adaptations based on Dijkstra's algorithm, there are ways to take care of this centralized requirement, and there are practical routing algorithms that do this in a distributed fashion. Note that the algorithm can run into loops when there is a link failure, of which not all nodes are aware. Exercise 7.6 in the textbook deals with this situation, so I recommend that you try doing that. That brings us to the end of this part of our routing lecture. In the next lecture, we will continue with talking about the Bellman-Ford algorithm.